Hey guys, so today I'm going to be talking to you about the binomial distribution. So binomial distribution falls underneath the category of discrete distributions and all are not discrete distributions. And all that means is that the values that the random variable can take inside of the distribution itself are positive integers and 0. And so if we have a binomial with the parameters n trials and p successes, then we are going to end up with the PMF, the probability mass function. And what this does is this tells us the probability that x is equal to some x, so that the random variable is equal to some number. And so this little x right here could be any one of these support right here. And so, for example, if we want to know the probability that f was 3, then we would have n choose x times the probability of success. And so we would have 3 successes. So 3 times 1 minus the probability's complement, or I guess it's the 1 minus the probability for its complement. And then you'd have n minus 3. And the reason why this equation takes fold will be explained in this problem right here. So consider flipping a coin 3 times. What is the probability that we get 1 heads? So when we flip a coin, there are 2 outcomes. And this is the whole basis of the binomial distribution, is that it's either one or the other. There's no in between. So either we get a heads, or in this case, we don't get a heads, which is the equivalent of saying tails, but for the sake of this, I want to say the complement of heads. And then after we flip that heads, we can either flip a heads again, or we could flip not a head or a tail. Same thing for down here. And then for our last branch, have this. So H complement, H complement, H complement. And so this tree diagram is going to show us why we have the n choose x at the front, because intuitively speaking, right, if we flip a heads 1 time out of 3, that means that we flipped 1 heads, and that means we flipped the tail twice. And if you look, this is the exact same thing as this equation up here, where instead of x equals 3, x is actually 1. And so you would have 1/2 to the 1, and then you'd have 1/2 to the 3 minus 1. And so that is where the second half of the binomial PMF comes into play. But then the binomial tree is where we get this n choose x. You see, because we could have 3 different ways to achieve 1 heads. We can either go, here, so go through here, here, and here. So we have heads complement, head complement, or we can go heads complement, then heads, and then heads complement, or heads complement, and then heads. So here's a desired outcome, here is a desired outcome, and here is a desired outcome. So we have 3 desired outcomes that we could get. And so hence the equation for this, for the PMF at f of 3 is equal to 3 times 1/2 times 1/2 squared, which ends up being 3/8. And that actually makes sense, because if you see there are 8 desired outcomes right here, and we selected 3 of them. So hence this matches up perfectly. So let us do a little bit of a harder question. So let's just say any particular urn has 10 balls. Let's say 4 are red, 3 are green, and 3 are blue. Now we want to know the probability that we draw, let's just say we draw 5 balls with replacement. All right, so let's just say I want to know the probability that I draw 4 red balls. So R is equal to 4, given I drew at least 2 red balls. So let's expand this equation further. Conditional probability will tell us that this is going to be the probability that R equals 4 intersect X. Oh, my bad. I should keep my variables consistent. This should be red is greater than or equal to 2. So given intersect red is greater than or equal to 2 over the probability that red is greater than or equal to 2. What I'm going to do is rewrite this. So the intersection of R equals 4 and R is greater than or equal to 2 is R equals 4. And I'm going to take the complement of this. So 1 minus the probability that R is less than 2. And using the, or just less than, not less than or equal to, just less than. So this denominator can also be broken up into 1 minus, and then the probability that X equals 0 plus the probability that X equals 1. So let's find our probabilities. So we need f of 4, f of 0, and f of 1. So I'm going to write f of 4, f of 1, and f of 0. Okay, so we have, even though there are 10 balls in the thing, that only tells us about probability. Our number of trials is going to be 5. So we're going to have 5 choose 4 times the probability of success. So the probability of success is going to be the number of red balls divided by the total number of balls. So 4 divided by 10. And we have 4 successes times the complement. So if this is red, then that means the complement must be everything else. And so, in other words, 1 minus 4 over 10, which is 6 over 10, which is what 3 plus 3 adds up to. Let me fix that, 0. And this is going to be raised to the 5 minus 4. And so this probability, this will equal, this 5 choose 4 is 5 times 4 over 10 raised to the 4. So this is going to be 4 over 10 raised to the 4th. And then this is going to be 6 over 10 raised to the 1, which is equal to 5. 0.07, sorry, 0.0768. F of 1, same thing, except I'm going to skip this intermediate step. So 5 choose 1 is going to be 5, and then 4 over 10 raised to the 1 times 6 over 10 raised to the 4th is 0.2592. And then for f of 0, it's going to be 1 times 4 over 10 to the 0 times 6 over 10 to the 5th, which is equal to 0.07776. And so to calculate the probability of r equals 4 given r is greater than or equal to 2, we're going to have 0.0768 over 1 minus 0.2592 plus 0.07776, which is equal to approximately 0.11583. So in other words, knowing that we at least drew 2 red balls, the probability that we drew 4 is 11.583%.